Hi, I'm Ben-Yaakov. This presentation is entitled Power Dissipation of a Gate Driver and TI's Blunder. I'm considering here a gate driver feeding the gate of a MOSFET, power MOSFET. There is a resistor in between to limit the current, and when we have the pulses at the output of the driver going up at a leading edge, we have a current charging the capacitance of the gate, and then at the trailing edge we have again a current in the opposite direction, which is discharging the gate. So in this presentation I'm going to consider the power dissipated in the gate drive chain that is here, and to examine the distribution of the power between the components in the chain, and then to point out to some errors in some of TI's documentation. So here is a simplified equivalent circuit of this situation that we are talking about. We have the driver, and then we have a chain of resistors, and this is the transistor. Now, usually the driver will have two MOSFET. Today it will be MOSFET. Used to be BJTs, but most of the drivers today have MOSFET. And it could be like two N channel, but then you need a high side drive, so many times it will be a N channel and a P channel. This will be a simplified approach. And then there is a resistance. I'm showing here one resistance for the two MOSFETs. In some cases it will be different resistances for the high side and low side. I'll talk about that. And then we have the series resistor, and this is now the resistance of the gate, because the MOSFET has a gate resistance, because there are many individual small cells in the MOSFET, in the power MOSFET, and there are very fine lines going from the input to all these cells, and these have resistance. So this is a lumped resistor representing the resistance of the gate. Okay, so as I've said, as we have these pulses coming in, we have the charge, this is the red one, and then we have the discharge, this is the black one here. Now the capacitance of the gate, in fact all the capacitances of the MOSFET are non-linear capacitances. It's not simple to deal with a non-linear capacitor, like how do you charge and what are the relationships here of a non-linear capacitor. So the best way to avoid it is just to forget about the capacitance and talk about the charge that you need to feed the gate. So here we feed this charge here, and since this charge is actually coming this way, so it is coming from the input, and therefore this charge times Vin is actually the energy that goes into this circuit. Now all this energy is lost. In fact, half of it is lost during the charging, and then the second half is lost during the discharging, because then you discharge this capacitor into ground, so all the power goes into these resistors. Okay? So the power that goes into the circuit is the charge times Vin times F, or of course Q times F is the average current. So by looking at the average current here in VCC, you know how much power is actually going to this circuit, and it's all sort of pushed by the charge that you need for the gate. Now, since the same current is passing through all these resistors, and I am talking about a simple case now in which you have a single resistor here, series resistor. Normally you'd like to have perhaps two, one with a diode for a fast turn off and a slower turn on. So I'm just simplifying it like this. I'll talk about the more complex situation later on. And since the current is the same in all of these, then the power dissipated by each one of these resistors is proportional to the resistance. So if I know the total power, this is the total power, then the power dissipated by this resistor is RD over the total, or the sum of all the resistors. Power dissipated here is again RS, and the same thing goes for the power dissipated within the transistor itself. So now let's have a look at the real transistor. This is an infinite power transistor, a hefty one, 120 amp. It's a lower voltage, 120 volt. And we see here that they are specifying the gate charge, the total gate charge, to be 158 nanocoulomb. And this is for a given operating point. And then they also give the gate resistance, which is 1.4 ohm. Okay, so this is information that the vendor is providing. So now let's see, first of all, if the model of the transistor, the LT-SPICE model, really holds up as far as this charge goes, because we are going to use it later on. So therefore, I'm going to actually examine the amount of charge that goes into the gate. So what I have here is a pulse source, which is representing the driver, high and low. It's 100 kilohertz. I have two resistors, but as you can see, I'm just using this 3 ohm. This one is blocked just to simplify matter. I mean, the resistance is much larger, so we can neglect the current here. And then I have the source, which is the current source, 100 amp, just for the same operating point. This is the catch diode. So when the transistor is off, the current goes this way. 60 volt as in the data sheet. And then I have here a behavioral voltage source, which is defined as the integral of the current going into the gate. So therefore, this is the charge that goes into the gate. Okay, so let's run it. And here what I see, first of all, let's start with this gate charge. You see that goes to high when charging, low, discharging high and low. And this value here is 153. And as you recall, the specified charge is 158. Well, that's close enough. And then I have here the total power that goes into the system. And this is, I'm getting it by measuring the voltage and multiplying it by the current of this source. So here it is. This is the current of the source, and this is the voltage of the source. And I'm getting here, but by using the LT-SPICE averaging option, I'm getting here that the average of this is 152 milliwatts. Now, if I do the calculation the other way around, I know the gate charge, I know the frequency, 100 kilohertz, VCC 10. These are the values, and what I'm getting from this calculation is 153, and this is 152. That's very close. Okay, and now I'm also measuring the power dissipated by the series resistor. This one, again, by multiplying the voltage and the current through it, and this is the time domain power. And taking the average, I found that this is 106. Okay, so we know that the total in power is 153. This power here is 106 milliwatts. So therefore, the difference is the power which is dissipated within this R sub G. Now, since the same current is passing through, then I can actually calculate RG from this ratio. And I'm getting it to be 1.33 ohm. And as you see here, it was specified as 1.4. So we can see that the model is pretty good, at least in these two terms. Now, what will happen if I have now a parallel branch here for a fast turn off, and if I have two resistors here? Okay. I'm not going to solve this thing completely. I'm just giving a hint of what to do. I think I have given enough background, so it's really easy to calculate it. What we have to do is the following. We have to separate the process into the turn on and turn off. In the turn off, we have half of the power dissipated, and during the turn off, we have half of the power dissipated. Okay? Now, These could be linear if this is MOSFET, but if you enter a nonlinear region, then it becomes really complicated and it'll be almost impossible to solve. So the best thing is to just assume a certain average linear resistor, or you go to simulation. We'll talk about it in a minute. And again, you have during the on, you have this resistance here, and during the off, you have this resistor, and then these two in parallel. You have to take into account the drop of the diode and this resistor. So this can be solved very easily. Same principle as I've shown earlier. For the interest of time, I'm not going to go into all the details here. But there is another issue here that we have not taken into account, and that is this fact that these transistors are switching, and therefore there are switching losses. Actually, there are a number of types of losses here. First of all, if this is a IC driver, then there is some bias current, quiescent current that you need for the unit. And then there are some losses during the rise time and fall time, and maybe some shoot through. So this is kind of a mystery here, and in fact, as we'll see in a minute, there is no data about that. So unfortunately, the datasheet does not give us enough information for this, and if really you're worried about it, then you'll have to test the unit itself in the hardware way, because we don't have enough information. So the best thing we can do without actually building hardware to test it is to use a model of the actual driver, and I've taken here a analog devices driver. This is the output, this is the input. There is another output which is called a slew rate control. I'm not going to use it. It's really beyond what we are talking about. It has nothing to do with the question of power, although of course you'll have to take it into account in the calculation, but I'm just neglecting it at all. Now this is a isolated driver. So there is a power supply here, and there is a power supply to the digital part, which I'm neglecting because the power dissipation here is just the current going in and the voltage. So this is 5 volt, by the way. So I'm not going into this part. I'm just talking about this part here. And what I have here is the same thing. This is the power supply for this part here. There are 2 transistors here. Actually, it's more than 2 transistors. We'll see it. And here is a 3 ohm resistor. This is the transistor. This is blocked at 2 mega ohm, and this is also just a bleeder. I'm also actually not taking it into account. And otherwise, it's the same thing. And I'm also looking at the gate charge, although we have seen it already. So this is a circuit we can actually examine the driver as much as the simulation model is correct. So here it is. I have here, first of all, the Q of the transistor, which is, of course, the same thing. There's nothing special about this one, 153 nanocoulomb. I have here now the total power coming in, okay? This is voltage and current. Taking the average, it's 209 milliwatt. And then I have the power dissipated in the resistor, the series resistor, 82 milliwatt. This is this resistor, the 3 ohm, so it's 82 milliwatt. And now we can do some calculation and see what's going on. Now, we know that the resistance, the internal resistance of the driver is 1.1 ohm. This is given in the datasheet, okay? And we know that the total power is 209, and the power dissipated in the 3 ohm is 82 milliwatt. Now, we found that the total power coming in is 209 minus 148 is 61. And so this is the power dissipated within this driver, okay? And this is taking already into account the power dissipated here, okay? This are these 30 milliwatt, Okay, so the 61 is just the driver itself. Now, analog devices give some information about the current that will go into the driver. This is the secondary side, IDD2, for frequencies, and this is with no load. That is not taking into account the effect of the current passing through the unit. I'm not talking about the resistive part, but the switching part. It's not taking into account. This is just open circuit. And they are saying that this is like 2.5 milliamp, and therefore for our case of 10 volt, it'll be 25 milliwatt. Okay? Now, this I can test. That is, I've disconnected these two. This also is made 3 megohm. So therefore, there's no current, actually no practical current here. And it is switching again at 100 kilohertz. This is exactly like the plot that we have here. And what I'm getting is that this is 54 milliwatt, not 25. Now, I don't know how to explain it. And then we are short of the total power that we have calculated, which is more than 60. So there's something missing there, and this might be the switching of the transistors. So as it stands now, we can calculate the resistive part very easily. And also we can get an estimate of the quiescent current for the unit. But this part here, the actual switching loss of the driver due to the current passing through it, which could be a high current, this information is not very well documented. So there is a question here. Now I'm coming to a reference design by Texas Instruments of a driver. This is a 2-channel driver, and as you can see, we have 5.1 ohm for the on and 1 ohm for the off, fast turn off, with a diode, of course. This design has a split power supply, plus and minus, so this is not important for our discussion. What is important is the total voltage, so we'll refer to the total voltage. And as you can see, the driver here at the output is kind of complicated. It has, here it is an N channel, which is of course easy because it's referred to ground and you can generate a voltage which is higher than the ground. But here it has a P channel, which is kind of limited in the current. So therefore they have another N channel, which as you can see operates only halfway, doesn't have a high side drive. Okay, so it's only starting at the beginning and then it's not functioning as the voltage goes up. So this is really a complicated drive, non-linear, and I'm not going into it because it's just too complicated and there isn't information about all these parameters. But what they are saying is that the high side is about 5 ohm, here it is, and the low side is 0.55, which is kind of reasonable because you like to have a fast turn off, okay? So therefore the resistance here is lower. Also this is N channel, this is P channel, so P channel, if the same size, will have a higher resistance. So let's see now how TI is suggesting to calculate the power dissipated, okay? So they say that first of all you have to take into account the quiescent power loss in the static condition, that is without the thing running at all, even not open circuit, just the quiescent, which is 72 milliwatt. Again, it includes the primary side, which is not of importance to us, and the secondary side. And then, now they are calculating the power loss of the driver is twice. Why twice? Because there are 2 channels, the voltage, the charge of the transistor, and the frequency. This is the total power coming into the driver as we've seen it. The voltage times the charge times the frequency. Twice of it is for the 2 channel. Now they're saying that this whole power is dissipated in the driver. This is not correct, because this driver has a 5 ohm in one direction, it has 1 ohm in the other direction, not to mention that there is a resistance to the transistor. So this is not correct. So they are using it, adding this to this for the total power as if it is dissipated within the driver, and from this they calculate the temperature rise, the expected temperature rise, knowing the thermal resistance. So this is just incorrect. I'm giving some credit to TI. It turns out that in some other publication they have, in fact in the datasheet of same driver, they have also a calculation of the power dissipated, and they are saying that this is twice, this is the total voltage times the charge times the frequency, which is okay, 2 channels, and they calculate the total charge going in, which is correct, and then they are splitting it to the on and off times, which is fine, and taking into account the resistances that they have during the high side and the low side, and here it is, and this is the 2 transistors that they have in the driver. This is the R-on series resistor, this is the gate resistance, this is for the on time. For the off time, they have the low side, and then they have these 2 in parallel. Well, the diode is not taking into account, that's okay, it's a good approximation, and then they have the gate resistance. So this is fine, but now they are multiplying it by 133, the whole thing. 133 is the total power coming in. Okay, now if you multiply the total power times this and times this, you're getting too much, because each one of these sees only half of the power. Okay, so in fact you need here to divide it by 2. So this is halfway correct, but here they missed the fact that you have to divide it by 2, because if you don't divide it by 2, okay, let's have a look at the other way, and suppose all the other resistors are 0 and only this counts, then you have 1 here and 1 here, and you'll have twice the power, which is not logical, because this power, the 133, is the total power going in. So we see that, well, it's halfway. That's good, more than nothing, but again, there is some error here too. So in this presentation, I tried to show how to calculate the power dissipated in the gate drive chain, and then how to divide the power between all the components, and to point out some of the errors in the TI documentation. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.